All right, Bismillahirrahmanirrahim. So on Thursday, we've already looked at the factors that affect selective discharge. The easiest ones, the number one factor that you should be looking at is their arrangement in terms of their standard electrode values. Okay, so cations, the most positive ones, will be discharged first, and anion, the most negative one, will be discharged first or will be selected. And then the second factor is the concentration. So you have to look out for the term molten state or concentrated. And the last one is the electrode, the nature of the electrode. Usually a non-inert electrode or a reactive electrode, such as metals that are reactive, they will actually affect the selection process, okay? In last lesson, we looked at question 1.1. Basically, if we use dilute sulfuric acid as our electrolyte, what would be discharged and what is the reaction that is happening at each electrode? Okay, so the first part we've answered. The second part, what happens at the anode if carbon electrode is used instead? Now you need to understand that carbon electrode is also inert. Okay, so that means the answer to question B, there will be no change. Okay, no difference. So since carbon electrode is inert like platinum, therefore same reactions occurring at both electrodes. Okay, so there's no difference there. Okay, everyone is here. Thank you.
That was the last, bruh.
Siapa
Okay,
kantor?
but
Ridwan. Come on, let's start class now. Okay. Next question is question 1.2, electrolysis of aqueous copper sulfate using carbon electrodes. Same thing. Carbon electrode is inert, so that means it doesn't have any effect on the selection process. Copper sulfate would mean that since it is aqueous, you have copper 2+ ions and sulfate ions. You also have H+ ions and OH- ions from water. Okay, so between copper and hydrogen, it will be, okay, so between hydrogen and copper, copper will be discharged. Copper will be selected, right? So you can always refer to the electrode potential of copper. Between sulfate and hydroxide, it will be the hydroxide ion. Okay. You can always refer to page 2 of your notes. And then we are to write down the equation occurring at cathode and anode. Same thing. Cathode is the negative electrode and anode is the positive electrode. Reduction happens at cathode, sorry. Reduction happens here and oxidation happens here, okay? So that means the positive ions will go to the negative terminal and we have to write down the equation for the reduction process, which is Cu2 plus gaining electrons, okay? Remember your oil rig reduction is gain in electrons and oxidation is lose electrons. Now, if you're wondering how to get the half equation, you can always refer to your data booklet. Copper is Cu, so you just have to be careful. Cu2 plus gain 2 electrons to form Cu. So that means if we are taking the reduction equation, we are taking the forward reaction. Okay, so this information is available in the data booklet. If in the exam you are given information on electrode potentials, use that list to find maybe there are half equations provided to you that you can use and you don't have to work it out yourself. Okay, as for the anode, okay, which is your positive terminal, it will be your hydroxide ions. Again, I never remember my half equation. I know that hydroxide ions will undergo oxidation. So if I just go through the list, hydroxide would be somewhere at O. Now you may be wondering if you're looking for hydroxide on this side, that's wrong because you are now looking at the oxidation process. Oxidation process is the reverse, remember? So you have to look at hydroxide on the right side, okay, on the right, on the product side. So you want to find the hydroxide ions that will produce oxygen as it is an element. Okay, so you see here 4OH minus to produce oxygen and 2H2O plus 4H plus, sorry, O2 plus 2H2O plus 4 electrons. Okay, so make sure you, hold on, is that correct? Yes. Okay, so that means it's 4OH minus to form O2 plus 4H2O, no, 2H2O plus 4 electrons, okay? So you have to take the reverse equation because remember that this list forward reaction will give you a reduction reaction and the reverse reaction will give you the oxidation equation. Are we all okay so far? Okay. Um, right. I also noticed that it says to uh, write down the observation. Okay, so we have to look at the products that are being formed, the elements that are being formed. Since we are forming copper solid on the negative electrode, we would observe a copper solid being deposited. Okay, so copper solid being deposited on the negative is cathode. On the cathode, at anode, bubble of gas produced. Okay, so our observation should be on the element, right? H2O, you cannot possibly see H2O being produced because it is in solution and you don't see electrons. So usually the observation applies for the elements that are being produced. Okay. Since copper is solid, you would expect that the electrode will have some copper coating around it. Okay. You understand the word deposit, right? It means that the electrode is being coated with copper. Okay. Next question is copper sulfate using copper electrodes. So this time copper electrodes. Now we're on question 1.3. I'll just leave this slide on just in case some of you are still copying it down. So question 1.3 is saying electrolysis of aqueous copper sulfate using copper electrodes. Okay, so I'll move on to the next slide. Okay, you need to highlight that copper electrodes is reactive and will get involved or will get reacted in electrolysis. Okay, so same thing, copper sulfate, it's still an aqueous solution. Oops, aqueous. So there's copper 2 plus, SO4 2 minus, H plus, OH minus. Don't forget there is also your copper solid. Okay, so what happens here is that your copper solid will be selected in this electrolysis process. Okay, and copper can only undergo reduction from copper to copper 2 plus. Okay, so usually reduction happens at cathode. Agree? Okay, so that means I have my positive terminal, which is anode, where, oops, where oxidation is happening. Okay, and then I also have my negative, where reduction is happening. Correct, right? Anode, positive, cathode, negative. Okay. So my copper will get involved. And copper, I only know because it's a copper, sorry, it doesn't go through reduction. My bad. It goes through oxidation. Okay. From copper solid to copper 2 plus. That's the only possible path for this copper electrode. Okay. Remember that copper solid is my electrode. So the only possible reaction is oxidation, which happens at the anode. Okay, so that means copper sulfate will be, bukan copper sulfate, copper solid will be oxidized. So I'm looking at oxidation here. Copper to Cu2 plus. Okay, it will be oxidized to ions. So that's why you have to be careful with the electrode. If we are using an electrode that is reactive, it gets involved and it somehow interferes with our selectivity. Okay, so copper will be oxidized into copper 2 plus 2 electron. Okay, and our copper is aqueous. As for reduction process, which is at the cathode, the selected cation will be Cu2 plus. Okay, Cu2 plus aqueous plus 2 electrons to form copper solid. Are you all okay with this? Okay. So that's the only problem with using a reactive electrode is that it will get involved in the reaction. Okay, the metal will react. So that's why when the metal reacts, it is being oxidized from copper to copper 2 plus. Now, if we want to talk in terms of observation, okay, we look at the observation at the reduction first, right? So we see that the aqueous copper ion will form copper solid, okay? So aqueous copper is blue in color in solution, and copper metal is usually like brown, okay? So don't think that copper as a metal is blue. It's copper ion that is blue, right? As for oxidation, our copper electrode is forming Cu2 plus ions. That means we are releasing blue solution, okay? But at the same time, our blue solution is also fading, all right? Because we are using and producing the same amount of copper 2 plus, essentially the change cancels out, okay? I repeat, here, if we have this oxidation happening, because of the formation of copper 2 plus, our solution, our electrolyte would appear light blue. Okay, the light blue is getting darker. At the reduction, our copper 2 plus aqueous is being used up to form copper. So, blue here darker, but here blue is lighter. Essentially, the effect cancels out. Okay? If something is getting darker and the other one is getting lighter, it cancels out. So technically, you will not see any change. Okay? So no change to the blue color solution, which is your electrolyte. However, of course, you will observe the cathode copper solid being deposited, okay, and the anode since the copper is being used up, the mass of the anode will decrease, okay, or the metal will start to thin out. So mass of copper solid will decrease because you're using up. Okay, so anode is positive, cathode is negative. Please correct me if I get it wrong at any point because I always get my labeling confused, especially with the cathode being negative, anode being positive, and also my oxidation and reduction. Okay, so just check as we go along. Okay, so I will let you copy that out. So this is the main difference if we're using a non-inert or a reactive electrode compared to if we use an inert electrode like platinum or carbon, where we would observe oxygen gas being produced. Is everyone okay so far? I believe this is also not something new. I'm sure you have already seen this before, where at one electrode you see the copper being oxidized and the other electrode you see the copper 2 plus being reduced. Okay, so next is 1.4, the last one, electrolysis of concentrated HCl. So the keyword that you need to highlight there is concentrated. Okay, so please make sure you highlight that. Using platinum electrode, so you don't have to worry because that's inert. Okay, so it will not affect your selectivity. So HCl concentrated means you have H plus and Cl minus in high amount. You also have H plus and OH minus in low amount. Okay, so for your cations, there's no issue really. Okay, because you only have one choice, which is your hydrogen ion. And at cathode, usually reduction is occurring, and at anode, usually is oxidation. Okay, so for the cathode, obviously it's the H plus. For your anode, however, you need to take into account of the concentration of chloride. Between chloride and hydroxide, if we follow the rules, the reactivity series or the ease of discharge, hydroxide should win. Okay, hydroxide should be discharged easily compared to chloride. But here, because chloride contains in a higher amount, chloride will be selected. Okay, so I will just write down first. At the cathode, it's the H plus being selected, and at the anode, it's the chloride ion. Okay, we're all already, hopefully, familiar with writing down the reduction half equation for hydrogen ions to form hydrogen gas. As for chloride, it's easy to work it out, but if you have the data in your exam, you're given the data, chloride would be Cl. Now, chloride undergoes oxidation, so we should look at chloride on this side, okay? Because we're now looking at the reverse reaction. So it's 2Cl minus to form Cl2 plus 2E minus. So it's 2Cl minus being oxidized to chlorine gas plus 2 electrons. In terms of observation, bubbles of gas will be observed on both electrodes. Okay, because we are producing chlorine gas and hydrogen gas on each electrode. So you would observe gases being formed. Okay, so that's all our practice for selectivity discharge. We will now move on to the second part. And this is going to be a new concept for you. The first part that we've looked at is actually just a revision of what you have already learned, but maybe you don't remember. Okay. Right. It is called the quantitative electrolysis. Okay, there's a typo there, but quantitative electrolysis means something to do with quantity. Okay, something to do with counting. All right, so you would imagine that there will be calculation. State and apply the relationship of F equals to LE, which is a new expression for you, between the Faraday constant F. So Faraday constant is a new constant for you, and the Avogadro constant. Avogadro is not new. You already know what Avogadro is, which is 6.02 times 10 to the power of 23. It is being given the symbol L, okay? And the charge on the electron E. The charge on the electron means the single charge of one electron, okay? I don't know if you remember this, but the charge of a single electron is negative 1.6 times 10 to the power of minus 19. Okay, the arbitrary charge of an electron is -1. Yes, -1. All right, but the exact charge in terms of coulombs would be negative 1.6 times 10 to the power of minus 19 per one single unit of electron. Have you come across the term the unit coulombs before? I think if you do physics, then you would know that coulombs is the unit for the quantity of charge. Okay, right. So first, I need to introduce you to the units for quantity of charge, which I think the physics students have come across this expression, Q equals to IT. Yes? Non-physics, have you come across the Q equals to IT expression before? Non-physics students. Macam Indah, or maybe you don't remember. Yadi, do you do
Yes.
physics?
Yeah,
Oh,
I
you
do
do
have.
physics. Okay, right. So quantity of charge, the symbol is Q. Okay, and the unit is C, capital C, and we call it the coulomb, right? Is the quantity of electric charge. How do we find the quantity of charge? During electrolysis, we take Q equals to IT, where I is the current in amperes. Okay, A. How about amperes? Have you come across amperes before? Amps, okay? Current in amps, and T is time in seconds. Okay, you must always convert your time to seconds if you use this expression. Okay, so that's a reminder for you in case you have, for those who have not used this expression before. Okay, for the physics students, they've used this a lot of times already, so it shouldn't be a problem to them. Okay, so if you multiply the current that you use from the power supply with the time you let the current to run, the number you get is the charge that is going around in your circuit, okay? So we can use this for our electrolysis. If you remember, our electrolysis is like a complete circuit, okay? Because you have a power supply here, and then the electrolyte is a conductor, so we can find the charge that goes around in this electrolysis setup using Q equals to IT. Okay, moving on. Oops. Okay, right. So you've already know the expression Q equals to IT. Next, we want to state and apply the relationship F equals to LE. This is again another new expression. None of you, I think, have seen this expression before, between the Faraday constant and the Avogadro. Okay, right. So Faraday constant is F, okay, equals to L times by E. So L is the Avogadro constant, the number of particles in 1 mole. Okay, and E here is the charge on a single unit of electron. That means if you can, theoretically, if you can take out one single electron, the charge on this one single electron is negative 1.6 times 10 to the power of minus 19 coulombs. Okay, so that's why we have this. Because electron is negatively charged, therefore it has a quantity of charge. Yeah, because it is charged. Just like your proton as well. Proton is positively charged. So proton also have a number, a value of charge that it carries. Okay, now you notice that we do not include the negative sign because F is supposed to be a positive number, is the amount of charge that 1 mole of electrons carry. Okay, so before I add in my L, which is my Avogadro constant, which is the number of particles of 1 mole, E is the charge per one single electron. If I multiply the charge of one single electron with the Avogadro's number, which is 6.02 times 10 to the power of 23, that means L times E gives me the charge of 1 mole of electrons. Okay, so 1 Faraday is just a short form of saying things like a pair of socks, where 1 pair of socks contain 2 units of socks, right? 2 pieces. Like a dozen of eggs. A dozen means it contains 12. Here, 1 Faraday means the charge of 1 mole of electrons. Okay, so you can try multiplying 1.6 times 10 to the power of minus 19 with 6.02 times 10 to the power of 23. You will not get the exact same number because it is a constant, and depending on the value that you use for your L, which is your Avogadro's constant, different people will get different things. In your syllabus, okay, so by calculation, I got 96,320. Okay, if I calculate it using my calculator, which I think you should try. Take your Avogadro's constant as 6.02 and take your charge of single electron as 1.6 times 10 to the power of minus 19. Calculate it on your calculator and you get 96320. Yes, okay, but for your syllabus, the Faraday's constant is stated as 96500 or 9.65 times 10 to the power of 4 coulombs per mole. Now, how do I get the units? Okay, F is equals to LE, correct? L is your Avogadro's number, which has a unit of mole to the power of minus 1. Okay, E is the charge of your electron. We will ignore the negative sign because the negative sign is just telling us whether it's positively charged or negatively charged. Okay, coulombs. The unit of the charge of electron is in coulombs, so coulombs per mole when you multiply them together. Okay, so if you can find this table at the back of your exam paper, please look through it, okay? Because sometimes it can help you with the units. Okay, what else do I want to write? Going back here, so 1 Faraday's is always the charge carried by the total charge carried by 1 mole of electron. Okay, it's just like me saying 1 mole of pen, which means that I have 1.62 times 10 to the power of 23 units of pence. Okay. Right. So what's the difference between Q versus F? Because Q is also the charge, the quantity of charge, and F is also the quantity of charge. Okay, Q is the amount of electric charge carried during electrolysis. Okay, because different system of electrolysis will depends on different current that you use, different time. So of course the charge Q will vary. Okay, it is not a constant depending on how long you let your electrolysis run and depending on the current that you supply to your electrolysis setup. Whereas F is fixed. F is the amount or the quantity of electric charge that is carried by 1 mole of electrons. Okay, Q and F are related to each other, which you will look at later on. So 1 Faraday for our syllabus is always 96,500 coulombs per 1 mole. Okay, so per mole, mole to the power of -1. Okay, but if you're talking about 1 mole of electron, then you don't need this. Okay, right. Okay. Mass. The mass of substance that is produced or removed from an electrode during electrolysis. So just now you saw that during selective discharge, we can either produce gases at the electrode like oxygen or hydrogen gas. We can also produce copper deposits, okay, copper coating on your electrodes. Or we can also lose mass in the case where your copper electrode is being oxidized. Okay, so this mass is directly proportional to the quantity of electricity. That means this mass is proportional to the charge in the electrolysis setup. So the bigger the quantity of charge, the bigger the mass of solid being deposited or the mass of solid being lost or the volume of gas being produced. Okay, usually if we talk about gases, we don't refer to its mass, we refer to its volume. Okay, masses is usually for apa ni, solids. Okay, okay. Um, right. So you need to remember this as well, that mass is proportional to charge, where charge is equals to IT. Okay. Okay, before we do the calculation, we also need to understand um, how many moles of electrons are involved in an equation. Okay, because we know that 1 mole of electron carries 96,500 coulombs of charge. Okay, so it helps that we know how many moles of electrons is either required for reduction process or released for oxidation process. Okay, reduction is gained in electrons and oxidation is lost in electrons. So if we look at the electrolysis of silver nitrate solution, where the silver is deposited, that means the silver ion is being reduced at the cathode. Okay, so when silver ion is being reduced to silver solid, 1 mole of electron is required for this reduction process. Okay, how do we know the number of moles of electrons? We refer to its half equation. Okay, make sure that it's balanced and make sure that it's the correct half equation. So you can see here to deposit 1 mole of silver solid, we require 1 mole of electrons. Do you agree? Based on the equation, okay? So, and we know already the charge carried by 1 mole of electron is 96,500 coulombs. So that means to produce 1 mole of silver, 96,500 coulombs is required. That's for silver, okay? Next, an example of the electrolysis of copper to sulfate solution. Again, at the cathode where reduction is happening, the copper 2 plus is being reduced to copper solid. So to form 1 mole of copper solid, you require 2 moles of electrons. This is the balance half equation for the reduction of copper 2 plus. So in terms of charge, 2 moles of electron would require 2 times 96,500 coulombs. So this time you need 2 Faraday. 1 Faraday means 1 mole. 2 Faraday means 2 moles. And if I were to calculate that, it would be 193,000 coulombs. Okay? So if you want to produce 1 mole of copper, you need to supply 193,000 of coulombs of charge into your electrolysis system. Okay. It works the same for anode as well. Anode, this time we're looking at oxidation reaction. Okay, oxidation occurs at anode. So if we have the electrolysis of molten sodium chloride, where we produce chloride gas, to produce 1 mole of chloride gas, we will release 2 moles of electrons. Same thing. 2 moles of electrons would have a quantity of charge of 2 Faradays. That means 2 times 96,500, which is the same amount, 1,093, sorry, 193,000 of Coulomb is required to produce 1 mole of chlorine gas. Okay, sorry, not required, but release electrons. Electrons release means you lose electrons in an oxidation process. But the numerical number of charge is the same. You will also lose 193,000 of Coulomb to produce 1 mole of chlorine. Next one is the aqueous solution of sulfuric acid. Same thing. If you want to produce 1 mole of oxygen, 4 moles of electron is being released. So the quantity of charge would be 4 times 96,500, which is 386,000 of coulombs to form 1 mole of oxygen. Okay, so you can see a lot of charge is needed to produce 1 mole of oxygen in the electrolysis of sodium sulfate. Okay, I hope we will have enough time to do at least one question so you know where this is going. All right. Okay, so that's how you know how much charge or how many charge in coulombs is required to form 1 mole of your elements, your products. Okay. Now you may ask, why are we not interested in the formation of water? Now water will only get mixed into the electrolyte solution. So we cannot measure how much water is produced. Whereas oxygen, because it's a gas, we can always use the displacement collection method, okay, where you collect oxygen gas using displacement of water. Okay, And other things like chlorine gas, you can also measure chlorine gas using the displacement of water. Copper solid, you can measure copper solid by taking the initial mass of the electron and the initial mass of the electrode, which is your cathode, and the final mass of your electrode, which is your cathode. So initially you don't have anything forming on your electrode, but at the end of the electrolysis, you will see that your electrode has increased in mass because there is now some copper solid being coated around your electrode. Okay, right. We'll do one question. Calculating the amount of substance produced during electrolysis. So the learning objective is that to calculate the quantity of charge passed during the electrolysis using Q equals to IT, the mass or volume, depending on whether it's a solid, mass, if it's a gas, volume, of substance liberated during electrolysis. Okay, liberated means give out. So the value F, the Faraday's, can be used to calculate the mass of the substance deposited or the volume of gas produced at an electrode. Okay, so how can we use Q equals to IT and F equals to LE in calculating how much product have we produced during electrolysis? Okay, so example 2.1. So you need your foolscap paper for this if you have not printed out your notes. Don't worry, as I said, I've already printed out your notes, but it's in school. So hopefully next week, okay, I'm hoping to come back to school next week, but maybe not on Monday because I just tested this morning. My ART is still showing double lines. So hopefully Tuesday or Wednesday. Okay, so today's my day 5. So I'll do another one on day 7, which is on Monday. And then if I'm clear, I can go to school. Otherwise, I'll stay until day 10. Okay, so I'll keep you updated. Right, let's have a look at example 2.1. Calculate the mass of lead deposited at the cathode during electrolysis. So cathode means reduction is happening. Okay. When a current of 1.5 amp flows through molten lead 2 bromide for 20 minutes. So remember, minute is not the units that we are interested in. AR of PB is 207 and the Faraday's constant is 96,500 coulombs per mole. Okay, first we start with writing down the half equation for the reaction. Lead undergo reduction. Okay, so it should go at PB undergoing reduction. Ano? Okay, so it's this one. Sorry. PB lead deposited. So that means PB lead is produced. Okay, so that means it's PB2 plus. Okay, sorry. So we should be looking at PB2 plus forming PB. Do you all agree with that equation? PB2 plus 2 electrons to form lead solid. So PB2 plus 2 electrons to form PB solid. Now, when you write down the half equation, you should use an irreversible arrow. Do not use the equilibrium reversible arrow, okay? So that means based on this half equation, it says find the number of coulombs to form 1 mole of PB. So based on this equation, we just okay. So to form 1 mole of PB solid, 2 mole of electrons is required. And 2 mole of electrons means 2 Faradays. Agree? Okay. That means 2 times 96,500 coulombs. So what I can write is to form 1 mole of PB solid, I require 2 times 96,500. 193,123 coulombs. Okay, so you need this later on for the ratio. Okay, step 3, calculate the charge Q transferred during electrolysis. Okay, so I want to know in my practical, in my setup, how much charge do I have around it? Okay, so Q is equals to IT, where I is the current 1.50 ampere times T, I need to convert into seconds. So please remind yourself to convert minute to seconds. You should get 1800 coulombs. Okay? Did you all get that? Okay, now the next part is important. Okay, remember just now I said that if I had 193,000 of coulombs, I would produce 1 mole of lead. However, in my electrolysis process, I only had 1800 coulombs. So how many moles of lead will be produced in my electrolysis setup? How do you think I can find that? I repeat, if I had 193,000 of coulombs of charge, I would produce 1 mole of lead. If I only use 1,800 coulombs, how many moles of lead would I produce? Okay, remembering in mind just now that the charge that you use in your electrolysis setup is proportional to the mass of the product or to the volume of gas that you produce. Okay, so the next step is that if I have 193,000 of coulomb, I can produce 1 mole of PB, but in my electrolysis, I only have 1,800 coulombs. So how many moles of PB would be produced for that much of charge? Okay, so you do cross cancel, and X would be Thank you, Ridwan. Ridwan gave me the answer. Let me just double check. Yes, 9.33 times 10 to the power of minus 3 mole of PB. The question is asking for mass. Okay, So here it's just mole conversion. Okay, mole conversion to mass. Mass of PB is equals to number of moles of PB times by the AR of PB, which is already given to you. The AR of PB is 207. Okay, so let's try. Times by 207. What is the mass of lead produced when you only have 1,800 coulombs of charge in your electrolysis setup? Okay, I just need to take a screenshot sekejap for attendance. Okay, are you all following so far? Okay. Can you share me the mass of PB being deposited? Oh, okay. All right. Okay, so just one last bit. Did you all get 1.93 grams? Okay, right. So that is all for today. I believe that some of you have your APR mats and you can go now. Okay, Assalamualaikum and thank you.
Thank you, miss.